Hello everyone. So I'm very happy to host Roi Livni here today with us. Roi is an advanced lecturer at the Department of Electrical Engineering at Tel Aviv University. His research focuses on theoretical machine learning. Today he will talk with us about online learning with simple predictions, with simple predictors. Sorry. So
is it באנגלית או
yes.
Okay. Okay, so thank you very much. So I'll be talking about this work. It was presented in Colt this year. This is a joint work with Steve Haneke and Shai Moran. Okay, so so this is a very kind of a simple model, nothing very fancy. Online learning, the mistake-bound model, where the idea is like this: you have a sequential game between what we call a learner and nature or adversary. And at each round, the learner gets to observe a point, xt, and it needs to predict the label. Okay, there is no distribution here, just a sequence. And then after the learner tries to predict the label yt, we get to observe the real label. Nature reveals yt, or in fact, nature can choose yt. And every time that the predictor or learner was wrong, you suffer a mistake. The learner suffers a mistake. And throughout this talk, we're going to make this realizability assumption where what the adversary needs to do, it has to be consistent with some hypothesis in with some concept or hypothesis in a concept class. So at the end of the game, there must be some concept in our class where the two labels chosen by nature are labeled by this concept. Okay, most of the results here are extendable to some agnostic setting, but I'm going to look at the realizable setting here. And what you want to do in this model is to avoid as many mistakes as possible. Okay. So let's start with a simple example. We can look at a game where you need to guess my age. I'm not going to tell you, but so the game is like this. You're going to consider at each round, I'm going to give you x between 1 and 120. I'm younger than 120. And the concept class is going to be for each possible age, you need to predict if x is above my age or below my age. Okay, so I'm going to ask you at round 1, am I above or below 60? And you need to guess whether, and you need to make as little as mistakes as possible. So let's say okay, so and you can pretty much see in this game that there's a very simple strategy where you're going to suffer at most 7 mistakes, or log 120, right? Because you can always make sure that if you made a mistake, then basically half of the possible ages are eliminated from the game. So maybe you're going to make 7 mistakes, but that's as much as you're going to make. Quick questions? Okay. So this is basically the general strategy you will have if you have this simple case where you have some finite hypothesis class, where what you're going to do is you're going to vote according to the majority. Okay, you have a lot of concept, each one guesses the real label, and if you want to make as few mistakes as possible, what you need to do is you just choose the majority. And what's going to happen is that at each round, either you are correct, so you didn't suffer a mistake, or the majority is wrong, and in that case, basically you can eliminate more than half of the hypothesis in your class. So the number of hypotheses is going to diminish by a factor of 2. So eventually, after log c mistakes, they're going to remain just one hypothesis, which you identified, and then you're not going to make any more mistakes. Okay. What happens if C is infinite? So now the notion of majority is no longer well defined, and you need to work with something else. So it turns out you can extend this idea to certain classes, which are called Littlestone classes, which have finite Littlestone dimension. And then it's not exactly a majority. I'll show the algorithm in a minute. But it works in a very similar way. So this was introduced by Littlestone in '88. That's why it's called the Littlestone dimension. And then, so we're talking about the realizable setting, which is exactly the setting. This setting was introduced in this paper, but later it was also extended to agnostic setting, and then it was also coined the Littlestone dimension, and so. Okay, so what is the Littlestone dimension? So the Littlestone dimension is very similar to VC dimension, but kind of like an online version of that notion. And it goes like this. You want to look at what we'll call shattered tree. So what is a shattered tree? So a shattered tree is a tree that is labeled by elements from your class. And then the left child represent labeling by 1. And the right child, let's say, represent labeling by -1 or 0. And then you look at this tree and you look at each path in the tree. And then at the leaf, you have certain hypotheses. And what you want is that this hypothesis will realize this path. So that means that, for example, hypothesis H2 labels X1 as 1, and it labels X2 as -1, because that's the path that goes to H2. And if you can build this tree at some depth, then we would say that this tree is shattered. Okay, and the largest depth of a tree that you can shatter, that is your Littlestone dimension. And it's kind of easy to see why large Littlestone dimension is a lower bound on the number of mistakes, because this tree kind of represent the strategy that your adversary is going to take. Because once you have such a tree, then your adversary can enforce at least 2 mistakes. In this example, by doing the following, it's going to show you X1. And then if you're going to label it, if you're going to predict 1, it's going to say, no, you're wrong. And it's going to go to X3. And then if you say X3 is 1, it's going to say, no, you're wrong. And he's consistent with H4, and so on. So for any path, any attempt of the learner to predict, the adversary can always go the opposite way on the tree and makes you suffer a mistake. Okay, so obviously the depth of the Littlestone dimension is a lower bound on the number of mistakes. And what Littlestone showed is that you also have a strategy for the learner. So if, yes?
What's the difference between Littlestone dimension and VC dimension?
Right, so the VC dimension, basically you would get the VC dimension if you won't allow, if at each depth, you get the same example. So you see here, you have, this set is not shattered because here I have X2 and here I have X3. These are two different examples. So if these were the same examples, then this set would be shattered. But from this, you cannot get that this is necessarily shattered. There is no shattered set here. Okay. So
VC dimension would be
and lower bound. So the Littlestone dimension will always be larger than the VC dimension. Yeah, you can always choose a shattered set, and then at each row, each row you put one example from this shattered set, and you get a shattered tree. Thanks for this question. Okay, so how do we learn classes with finite Littlestone dimension? So the idea is like this. It's kind of similar to majority, but it's not. But what you do is at each iteration, you're going to look at the concepts that are consistent with the examples that you saw. Okay, all other examples can be thrown away. And then you're going to divide them, given a new example. So sorry, this is xt plus 1. And then what you're going to do, you're going to divide them into 2 sets. Those that suggest that you need to label the new example by 1, and those that suggest that you need to example the new example, xt plus 1, by 0 or minus 1. Okay? And what you can pretty easily show is that one of these one of these sets is going to have a smaller Littlestone dimension. Okay, otherwise, kind of by induction, you can build a tree that has depth h plus 1. So one of them is going to have smaller Littlestone dimension, and we're going to think of this as being a smaller set. This replaces majority by the Littlestone dimension. So again, what you're going to do is that if one of these classes has the same Littlestone dimension as the original class, okay, maybe both of them has smaller Littlestone dimension, and then it doesn't matter what you choose. But if one of them has smaller Littlestone dimension, then that's what you're going to predict the one. Sorry, if one of them has the same Littlestone dimension, you're going to predict according to that class. And then again, either you don't make a mistake and then you don't care, everything is okay, or if you made a mistake, you learned something, and the new class that now you're going to work with has smaller Littlestone dimension. So every time you make a mistake, the Littlestone dimension diminishes. So overall, you're not going to make more mistakes than the Littlestone dimension. Okay. Questions so far? Okay, so something that is a little bit weird about this is that this algorithm is very improper. What does it mean improper? You have a class that you want to learn. You know that the true hypothesis comes from that class, but whenever you make a prediction, your prediction is not from that class. Okay, you take a set, an ensemble of possible solution, and then you look at something like the majority vote, and even that's not true. Like it's more complicated than a majority. And basically, your prediction is not consistent with anything in the class. So even though you know that the true solution comes from somewhere, eventually what the type of prediction you make is not consistent with the class that you're working with, which is a little bit weird, and makes you wonder, is it in something inherent? Could I somehow learn by actually choosing an hypothesis from a true class? Which is, yes, so you had a question?
Yes, in the finite case, you could end up with one hypothesis. Right?
You could, yeah. You even also in the infinite case, if you make LDC mistakes, it means that you end up with a single hypothesis. Okay, but this is just potentially if you made enough mistakes. Most of your predictions are not according to the class.
What you care about is what you output or what the predictions are along the way.
I don't care. What you care about is what you care about. You can care about both. So yeah, both are okay questions, but like there is no guarantee that at any time you're gonna make as many. You know what? If you had a guarantee that says after these many iterations you're gonna make these many mistakes, and you end up with a single hypothesis, and I would sleep at night. But even that is not guaranteed. So even the output of the algorithm at the end can be something very okay. So this is a very natural question. Like, when can I actually learn the class properly? Okay, I want to actually output not just I don't just want to make as few mistakes as possible, but I actually want to learn the hypothesis in the class. So there's a very simple, and overall, you would like to know when can you learn a certain class by looking at another class. And it's kind of it's a very simple example that shows that proper learning is actually not possible in this set. And the example is just if you take the singletons. So each hypothesis in your class gives one example to just one example in your class, and 0 to all the rest. And then if you enforce the learner to actually choose such an hypothesis, then the adversary has a very simple strategy to enforce infinitely many mistakes. So at first round, so the learner starts with some hypothesis, some base hypothesis, let's say delta x1. And then the adversary says, okay, x1 is not 1. So you have a mistake. So now the learner has to choose another hypothesis from the class. So he has to point on another example that he says, this is one. And then he suffers a mistake again, and so on. So overall, any proper learner will have infinitely many mistakes in this model. Yes? Right. So okay. So it is realizable on any finite sequence, right? Because on any finite sequence, at the end, I can say delta x. I have this point x that did not appear in the sample, and that's my delta x. Okay. So as long as you see just zeros on a finite set, it's realizable. And this is exactly what the online learner has to do. It has to say zero on everything until he sees something that is one, and then he identifies the hypothesis. But if you enforce him to be proper, he cannot do that, and then he suffers a mistake. Okay. By the way, there is a very simple fix to this by just allowing the learner to choose a randomized hypothesis, right? They can choose, let's say, that he will take. So if I look at the probability distribution over the deltas, then I can basically simulate something like zero every, right?
Can you explain again why in the proper setting the learner must choose one, must pick map one?
It has to pick some. It has to always choose some hypothesis from a class. So these are the hypotheses. So at the beginning, it has to say this is my hypothesis. There is some strategy, and it chooses something.
It tells the nature what is.
It doesn't. You can look at it as if it tells the nature, but nature knows your strategy. Okay, nature can be there. Okay, questions? Okay. Okay, so we showed that given a class C with finite Littlestone dimension, we can learn it via a class H of all the, let's call it SOA induced functions. Okay, there is a class that can learn my original class. I have to do improper learning. I cannot just choose something from do proper learning. And this raises these two questions, which we kind of answer in this paper, which is when can C be learned via H? So you don't tell me the SOA function. You say, I want you to return a solution from this class, H. Can you do it? Can you learn C through H? And a very related question is, when can C be learned by the closest thing that you can think of to proper learning, which is randomized learning, right? Like something like a majority vote. Because then basically you can think of this case as just another question. When can you learn using a majority vote, right? Because a randomized learner is just doing a majority. Okay. Okay, so let's go over the general framework just so that everything will be set in place. So we have a sequential game between learner and nature. Each round, learner gets to observe xt and needs to predict ht xt, where age comes from some class H. And H can be majority vote, can be the class itself, whatever you want. Nature reveals yt and you suffer a mistake as before. Okay, the only difference is now that I enforce the learner to choose age from a given class. And we're still going to make this underlying assumption that everything is realizable. Okay. So our first result in this paper is that there exists an online learner for the class C that uses predictors from the class H, and it makes L times K mistakes, where L is the Littlestone dimension of the class. We know that the Littlestone dimension is a lower bound, so it has to appear. And K, sorry, K is a dual Helly number of C relative to H. I'm going to explain what is a dual Helly number in the next slide. Okay, but for now it's just a combinatorial size. And what this means is that learning C through H is characterized by these two terms. Okay, and so the previous works were actually showed that our improvement is basically to show that the dependence can be linear in both, okay, at the same time, and not k times. Before that, it was known that you can learn in k to the power of L mystics. And there is a lower bound that shows that this is optimal, but it's not. By the way, it's not a. It's a lower bound that says that there are classes that you need L times k. Okay, there are also classes where you can learn with L plus k or things like that. So it's not a lower bound for any class. But if you look at what you might achieve for any class, then this is optimal. Okay. And so, okay, so what is a dual Helly number? So the dual Helly number of a class C relative to age is the smallest k, such that whenever you see a set S that is not realizable by age, there exists a subset of size at most k that is also not realizable by C. So that means that whenever something is not realizable by age, you kind of have a witness or a proof that it's not realizable by k that is by C that is not larger than k. Okay, just as an example, so let's take the class of singletons, but also I will allow you to label it by 0 because we know you cannot learn improperly only singletons. But now I add also the 0 function. So I allow you to, so you want to learn the singletons, and you can return a solution which is either a singleton, but you're also allowed to return 0 everywhere. Okay, we saw that basically if you look at the SOA, this is the compromise that you need to make. So in that case, every time some set is not realizable by this hypothesis, you have to have at least two points that are labeled as 1. So that are labeled as 1, which means that you have these 2 points which already prove that the sample was not realizable to begin with. Okay, so the dual Helly number here would be 2. Okay, there are some eyebrows that are shrinking, so I'll stop here and wait for questions. Okay.
Can you explain it again, please?
Okay, so I want to show that the Helly number, the dual Helly number of singleton with respect to singleton plus 0 is 2. So what do I need to do? I look at a sample that is not realizable. Okay. And then I claim that if the sample is not realizable, I have 2 points that are labeled as 1 because it is not all zeros because all zeros is realizable. And it's not just a singleton because singletons are also realizable. So it has to have at least 2 points that are labeled as 1. And these 2 points are proof that you cannot label it, that the sample was inconsistent to begin with. Okay, just to make it clear, let's say that, again, we return to the example where you need to properly learn the class. So now I want to learn the singleton with age. So now I have this set which is not realizable, which are all the whole points. Everything is 0 is not realizable, but there is no finite sample that can prove it. Every time I see a finite sample, there's always the chance that the true hypothesis is a point outside of my sample. Okay, so the dual Helly number of singleton with respect to itself is infinite, and we saw that we couldn't learn.
So it should be at least k, right?
Small, at least, why at least? You want to find the smallest case that satisfies.
Okay.
Okay. Okay, so this is our first result. And then we use this result to basically answer the second question, which is when can we learn through majorities? Like so this was a little bit weird to begin with, that when you look at the SOA algorithm proposed by Littlestone, it was it looks kind of weird. Like you have the finite case, you solve it through majorities. And then in the infinite case, you can solve it, but now majorities are not the solution. And it makes sense that you could somehow always solve using a certain set of majorities. And we show that indeed, you can always learn the class through majorities, and the majorities of P concepts, where P will depend on the class C. Okay, so it will actually depend on the VC dimension of the class. But you can actually learn through majority, which is you can think of it as the closest thing to proper learning that you can hope for once you cannot do proper learning. And as a corollary, you can also get that you can basically learn the class using a randomized proper learning. Okay, whereas the connection between a majority and randomized learning is kind of intuitive. Okay, so you don't, a simple majority might not be enough. You need to make sure you have a very large majority, but the same proof actually shows that not only you can learn by majority, but you can actually demand that the majority will be as high as possible. So you want to learn using a majority where 99% of the concepts are correct, or 99.9999 concepts in your class are correct. Then you can do that. And once you can do that, then you can also make sure that the number of expected mistakes you're going to make is going to be very small, because at each round you can just sample one of the points in the majority, and most of them, a large quantity of most of them, is going to be correct. And yeah, and like I said, this result can be extended to the agnostic setting. Because we're in the agnostic setting, you're not going to assume that some hypothesis is correct, and you're going to measure your regret. And actually, if you look at the result about majority, then there were already previous proof for online learnability with randomized learning. However, they were non-constructive, and they did show some existential proof. And they weren't, you could not get a bound on the number of majorities you need. And the second, and the last thing, which is the next slide, is they all relied on some properties of the class. You had to assume some, you had to, I'll show it in the next slide, but you had to assume that you can apply a Minimax theorem, which is something that we took off the proof. Which brings us to the last result, which is kind of interesting by itself and has nothing, well, is not really not necessarily related to learning, but it kind of made everything very simple in our proof, is a new min-max theorem. So what is a min-max theorem? You are familiar with the min-max, right? Okay, so this classical min-max theorem says that if you are given a finite matrix M, you have maximum over distribution from the left, maximum over distribution from the right, then maximum mean equals min-max. So in a game, you have two players. If I know your strategy and then I need to pick my solution, or you know my strategy and then you pick and you want to maximize, I want to minimize, it doesn't matter. There is a value to the game, and it doesn't matter who starts. And there are a lot of extensions to this. It can be extended to general games, but usually what you want to do is when M is an infinite matrix, you require some topological structure from your, let's say, matrix. So like classical result by Sion says that F needs to be convex in X and concave in what? Concave in X and convex in Y, and you need I don't know, you need semi-upper continuity, something. One of them needs to be compact. I don't even remember myself. It's in Wikipedia. You can find it. And these sets need to be convex. So these are results, and very naturally, a lot of games do have infinite game. But also, it's kind of easy to see that it's not a general result. Not every matrix will have a min-max. Okay? The simplest example is a game where I need, we play a game where I need to choose a number that is larger than your number, and you want to choose a number that is larger than mine. So if you start and you tell me your strategy, you're going to choose some distribution of the numbers. So I'm going to choose a number that is just going to be bigger than anything in your support. And then I win, and it's a completely symmetrical game. So if you start, you're going to do it. So this game doesn't have value. And it turns out that in some sense, this is the only obstacle. And by the way, you can think of this game as basically the threshold game where you don't have finite Littlestone dimension. And this is what we got. We basically showed that for any matrix M, so you can think of it as a case where rows are data points and columns are concept class. If M has finite Littlestone dimension, then it says then here, then M has a value. So that means you have a min-max. Okay, so whenever this matrix depicts a game with finite Littlestone dimension, there is a value, and it's a very nice result because I don't know. For me, it makes sense that you will not need to make topological assumptions on a matrix in order to decide whether it does or doesn't have a game. Okay, so in that sense, like this kind of made even these results, these randomized and non-constructive proofs, a little bit easier to handle because now you don't need to make these strange assumptions about the Littlestone game in order to apply these min-max theorems. Okay, so this is basically the proof main result section. Now I'm going to go into a little bit about the proofs. So if you want to ask questions.
No?
Okay, so a little bit about the proofs. Okay, so how do we show that? What am I going to show here? That you can always learn a class through a class H. Okay. So basically, the idea is going to be, it's kind of a combination between SOA and expert advice or weighted majority. But the idea is like this. So what we're going to do is at each round, we're going to consider an ensemble of SOA learners. Okay. At the beginning, we're just going to apply SOA. I'll tell you in a minute how you're going to do it because it's not proper learning, but you're going to start with that. And then with time, you're going to have more and more, somehow you're going to have more hypotheses. And what you do is you take their weighted majority. And a technical notion that I will need in order to explain the proof is what we will call the high vote of the class Q with respect to the parameter eta, which is, it's a sample, okay? It's not a predictor or something. It's a sample which includes all points that my predictor is has a very, very large confidence over, okay? Where very, very means eta, okay? Either it's almost as close to 0 as eta or almost as close to 1 as eta. But whatever the Q predictor chooses, the high vote represents the sample on which this predictor is very certain. And then basically the proof is going to rely on standard like potential argument. It's very standard in the setting, like the multiplicative weights also works like that, where at each round I'm going to hold weights, which are the way I'm weighting my hypothesis. And then what you're going to show is you're going to show two lower bounds. First, you're going to show that every time you make a mistake, the potential function, which is the sum of the weight, will decrease. On the other hand, you're also going to show that eventually there's going to be some hypothesis in your class where the weight did not shrink too much, basically because this hypothesis is very correct. So you're not going to punish it, and then it's not going to be reduced too much. And then because the number of mistakes is bounded, because this guy doesn't decrease too much, and every time you make a mistake, this guy does decrease. So overall, you cannot make too many mistakes because Wi star, because this is the sum of these weights, has to be always smaller. So at some point, basically the weights are going to identify the true hypothesis, and then you're going to stop making a mistake. Okay, and unlike the start, so this is basically how you prove multiplicative weights. But here it's going to be a little bit more subtle and convoluted because you're having an ensemble of hypotheses and they continue to change. And also you cannot really make the prediction according to this predictor because it's not in your class. So this is what we're going to deal with here. So now I'm going to actually go into the algorithm. And the idea is like this. So what you want to do is you want to predict according to Q. Okay, so remember Q is a predictor which is a weighted majority of SOA functions. Okay, but you don't want to make SOA functions. You want to make prediction according to class H. So the first thing you're going to check is basically, can I actually realize H, Q, using my hypothesis class? If this function is realizable in my class, then I'm okay. I can just use it. So you're not going to even have to make it realizable. You just need it to be realizable on this set of high votes. So if it is realizable there, then basically you're going to use a predictor from this class. Okay. So now you used some H from H to predict. What happens if you make a mistake? So if you made a mistake, if you didn't make a mistake, then everything's okay. Yeah. If you did make a mistake, you're going to punish all the hypotheses in your class which made the mistake. And you're going to update your hypothesis to only those that are consistent with your hypothesis. You can think of this as if you're locally applying the standard SOA algorithm, and also you have a weight which represents how much this hypothesis is not making a mistake. Now, because what you got is that if you made a mistake, then on high vote, you're not going to make a mistake. What you basically get is that anytime you make a mistake, basically you made a mistake on a point where the hypotheses were not very secure. So that gives you again that more like you will have a big fraction of hypotheses which are actually making this mistake, which would mean that the sum of the weights is going to diminish. Okay, I'm not going to go into the calculation by how much, but at least it's going to diminish by plenty. Okay, is it clear? Now you need to basically deal just with a case where you could not realize Q using H. And that's where you start making new hypotheses. So what's going to happen is whenever high vote is not realizable by H, I cannot actually find H that agrees on this sample. Then now, because of the small dual Helly number, it means that also I have in my sample a set of points which are not realizable in my class. Because that's where the dual Helly number gets in. I actually can find K points where you cannot label them according to any hypothesis in your class. And that means that okay, so I don't know which one so this is a non-realizable sample that my predictor makes. And I don't know where he makes this mistake because I didn't see actually the predictions here. But I do know that on one of them, he does make a mistake because it's not realizable. So he cannot be correct on all of them. So what I'm going to do is basically I'm going to guess. I'm going to guess on which one of them he made a mistake. Or alternatively, I'm going to like add a concept that takes into account the possibility of having a mistake on each and every one of them. I'm going to simulate as if x1, y1 is a mistake. or x2, y2 is a mistake, or x2, x3, y3 is a mistake. And for each of them, I'm basically going to take my concept and I'm going to update it as if it made a mistake here. And in that way, I split my original concept to k concept, where each of them also I diminished its weight because I gave it a mistake. I did not see that mistake. I'm just guessing it's a mistake. But the important thing is that one of these concepts actually showed a real mistake, because one of them is really a mistake. On one of them, you do have a mistake. So I still hold one concept that is correct in the sense that it suffered a true mistake. But I don't know which one of them, so I hold all of them. Okay, so I keep my game with all of them. So that means I increased my number of hypotheses. But on the other hand, each of them suffers a mistake, so each of them has some diminishing. And overall, if you choose your weights correctly, you get that, yes, you did increase the number of hypotheses, so that increases the weight, but you also diminished it. And you can balance your parameters correctly so that eventually, even in this situation, the weights are diminished. And then what you can show is basically that using the fact that one of the hypotheses is never wrong, so it did not diminish too much, you can bound your number of mistakes, but you can bound the weights using the number of mistakes plus the realizability, the number of rounds that you simulated by yourself, which allows you to bound the number of rounds that everything is going to happen. And overall, it will also give you a bound of the number of mistakes. Okay, so it's more complicated than the exponential weight, but very, very similar. Okay, so now how does it imply also that we can learn using majorities? So remember, this is the second result, that you can always learn by a randomized learner. So now the basic idea is just to show that I can choose a number on my majority where I will have a finite dual Helly number. So yeah, so we want to bound dual Helly number. So the idea is like this. So how do I bound it? Suppose F is not realizable by a majority vote, because that's the situation that what we need to show. We need to show that if F is not realizable by a majority vote, I can find a finite sample of bounded size that proves that you cannot realize this sample using some concept in your class. So basically, I'm in a case where for every distribution, I have a point xfx where the probability that cx doesn't equal fx is larger than half or larger than even 1/4, right? Because I cannot choose, the probability here is your majority vote, you choose some majority vote, and the claim that it's not realizable means that for any majority vote, you can always find some point that the majority is wrong. Okay, so this is basically the statement that F is not realizable by a majority vote. And then you can use the min-max for Littlestone matrices. Okay, so this is why we needed to prove that every Littlestone matrix has a min-max. And the min-max says that there is a distribution so that for any concept in your class, Fx doesn't agree with Cx with probability at least 1/4. Okay, so now I almost have what I want. What I want is a sample that proves that F is not realizable. But what I got is a distribution over points. What I'm going to do now is I'm just going to discretize this distribution. If you subsample D and you use uniform convergence, then you get that you can easily find an empirical distribution, and you can bound the side of this empirical distribution that already doesn't agree. So I found a sample where every concept is wrong. Okay, so it's a little bit, I did hide a little bit of things because of measurability issues. You need to assume that this D is finite, but all of this is taken care of in the paper. Okay. Yeah, I had two versions of this last slide and I didn't delete. Okay, so this is again the same statement. Okay, so this is it. I think, yeah, okay, in time.
Any practical use?
Practical use of the Littlestone Dimension? Yeah, it's privately learnable, right? Oh.
So this generalized Minimax theorem that you had, was that an if and only if statement?
Okay. The Minimax?
Yeah.
Yeah, it's a good question. Not exactly. The thing is, we know. Yeah, so if M has finite Littlestone dimension and M has value, if it's not finite Littlestone dimensions, there are two cases. One is that you have a subset of arbitrarily sized, finite subset of arbitrarily sized with each one of them is with finite Littlestone dimension, but there's no bound. So if you go back to the tree, it means that you have a shattered tree of arbitrary size, but there's no infinite tree. Because this is one case. And the other case is where you have an infinite tree that is unbounded. If there is an infinite tree, then there is no min-max. And we don't know, yeah, so this is an open question that we don't know. What happens in the middle if there are arbitrary size trees, which means the Littlestone dimension is infinite, but maybe there is a, so yeah.
So what would happen if you kind of try to take runtime considerations? Like, can you do something similar with okay, maybe first of all, so what's the runtime of your algorithm?
Right, so the SOA algorithm is very abstract. So you divide the class and then you calculate the Littlestone dimension of this division. So this is a part where you need to give me a computational model even to start working and describing what is the complexity, but this can be arbitrarily hard. So there is no runtime. Let's say okay, now let's say you give me this. So you give me an oracle that tells me the Littlestone dimension of these classes. The second obstacle is now here, right? Yeah, so you see now you need to choose whenever height Q is realizable by age, you need to predict. So that means you need to now take your hypothesis and check if you can realize it on this set using age. So again, now you can write a linear program that does it, but it's an infinite, like it's really abstract. So you would also need some oracles that solve this. And then everything is going to be polynomial in the Littlestone dimension. Yeah, so
choosing this set is
right. Okay. Yeah, and then finding right. Also, yeah, you need to find this witness. Yeah, it's very far from actually from an actual algorithm. It's just let's say it's information theoretic bounds.
Thank you again, Ray.
Okay.